Hartmann at UC Berkeley on the Toastboard, a novel tool for hardware debugging. And by hardware, I mean specifically breadboarded circuits here. So why do we want to help with breadboarded circuits? Well, anyone who's used a breadboard for some length of time can tell you that debugging is difficult and time-consuming. So imagine a world where your debugging process looks more like this, where the measurements are taken as you construct your circuit, provided to you both qualitatively and quantitatively. You can construct a virtual circuit model, and then you can use that virtual circuit model to automatically diagnose some common errors in your circuit. So guided debugging. Okay, but how do we get there in the first place? We're in it, the hardware renaissance, and hopefully some of the cool projects at UIST have convinced you that that is the case. These 4 pictures are from class projects at the Jacobs Institute of Design at Berkeley, where we're educating a whole new group of students, often without traditional electrical engineering backgrounds, on physical computing. So these are great. They've been enabled by tools like the 3D printer, the laser cutter, the Arduino platform. Yet if you look closely, all 4 of them share one common component, and that's the breadboard. So in 1920, this is what a breadboard was. It was literally a piece of wood that you drove nails into, and then you wrapped wires around the nails to make connections between components. In 1970, that switched to this, the solderless plug board that we know and love. This greatly speeds up prototyping, but it still has some issues. So for those unfamiliar, this is a breadboard. The back is a bunch of metal spring clips in the plastic body, and what it does is it creates electrical connections horizontally along the rows and vertically in the power rails. So this is great. As I said, it sped up prototyping, but debugging still remains a challenge. So can you find the bug in this breadboarded circuit? It'll be difficult, so I'll wait a little bit. Yeah, so maybe just in the corner there's like a wire loose, and you just spent 3 hours looking for a loose wire. And you didn't really learn anything about your circuit, about electricity. You just learned that there was a loose wire. So that illustrates the problem. I mean, this is an admittedly complex circuit, but this is a common problem with breadboarded circuits. So a paper this year at CHI noted that while professional software development tools have debuggers that help people locate and fix faults, there's no analogous tool for physical computing. We hypothesize that debugging is therefore difficult because much of the state of the system is both hidden by default and difficult and slow to examine. So what do I mean by difficult and slow to examine? Well, this is the most common tool used for debugging circuits. It's the multimeter. For those unfamiliar with the multimeter, you use those metal probes to physically touch places where you want to measure. And that first point, physically challenging because you actually have to touch what you want to measure, and the more complicated the circuit, the more issues that can cause. But more importantly, these are point measurements. So at one point in time, at one specific part of your circuit, you're making one measurement. And that leads to our new standard debugging pattern. So we've established this through interviews and our own experience. This is how people debug circuits. They form a hypothesis, so why doesn't my circuit work? They make a measurement plan of how to attack that hypothesis, and then they take those point measurements, which can take a lot of time, and then they collect those point measurements to evaluate their hypothesis, finally. Now, if they're wrong, they're back to square one. They have to form a new hypothesis and then collect a whole new set of point measurements. But if our system can make all the measurements for the user and provide them with low effort on their part, it would become more a case of forming a hypothesis and simply observing the given system and then evaluating it. But we can take that a step further. We can actually supply a likely hypothesis, and then it really comes close to that ideal of just observing and evaluating rapidly. So there's been some progress in this field. On the left there is the visible breadboard, and that was presented a few years ago. What it did was made the electricity that's normally invisible visible with LEDs. So the problem is that it's incompatible with standard circuit components. It's a fully custom design, and you can't plug normal IC packages or something into it. It also focused on construction rather than debugging. So their user study quantified the time it took to construct a circuit versus debugging it. On the right, we have the Digilant Electronics Explorer board. This is an expensive retail board. What it does is it brings some of the instrumentation closer to the breadboard. So we have multimeters and oscilloscopes right next to the breadboard. However, you're still making point measurements, so you're still connecting one wire at a time to where you want to measure on the breadboard, and there's no visual feedback on the board itself. So we saw that, and we thought that there had to be a better way, so we created the Toastboard. Okay, right. So the Toastboard features ubiquitous instrumentation. What we mean by that is the entire breadboard is instrumented, and we provide the measurements with low effort on the user's part to them. And then we get multiple means of access to the information. So they have the visual LED bars on the board, and they also have a software client with more information. We can combine those physical measurements with some virtual models to automatically diagnose common errors in circuits, getting to that observation and evaluation loop I talked about earlier. And the users get to keep their current breadboarding practices because they're still building circuits on a breadboard. So I want to walk through the features of the system. This is the front-facing hardware, and alongside the board there are these LED bars. A red color indicates a power connection, green for an intermediate voltage, and orange for ground. So that's just at-a-glance information. There's also some ancillary features. There's just status LEDs for if the device is on or if it's sending data. There's a button so you can use the device if it's not connected to a software client, so it could be standalone. This is the software client. You can see it has a lot of features, but for now we're going to focus on the virtual breadboard. So here, we can scan the board once, and it will populate the entire breadboard, or we can scan it continuously, where the entire thing will refresh at 200 hertz, so almost real time. And that data will be displayed color-coded and quantitatively alongside the board. Now I'll show a video of me constructing a circuit on the Toastboard while continuously scanning. So you see as I place components, lights along the board come on, and also that virtual breadboard is populated with the readings. So I've already provided some benefit to the user. I've made all those measurements for them, but I can do more than that. By populating that virtual breadboard with virtual components from this, you just take a drop-down menu, point and click, and you construct your circuit. We can add some more functionality. So let's look at what that looks like. So now I've built a virtual representation of that circuit I built earlier. And what I can do is I can combine the physical measurements with that virtual model to create something we call checker functions. So this helps to overcome the knowledge barrier of debugging, where you need to know what a likely hypothesis is before you can form it. You need to know what could possibly be wrong in your circuit. So we can preemptively provide that information to the user and tell them what we think is wrong, and then guide them to fix it. So our checker functions can diagnose errors, as I said. So for instance, here it notes, because of the voltage across this virtual LED, it notes that it may be backwards or it may be broken, and it tells them how to fix it. But they can also just provide information. So it can tell the user the current through a resistor they've placed just based on the voltage reading. So that's information for free up front to the user. This is an example of those checker functions. So I introduce an error into the circuit by reversing the LED. And you can see that's propagated to the virtual model where I have the new error function. I also see there's no current through the resistor. And by fixing the problem, it clears in the client, and I get that information, the current through the resistor. In the second example I'll show, it's just an off-by-one wiring, so very common when breadboarding circuits. You can see it from the lights on the board itself. We can also see it from the error function on the right. Then when I fix the problem and scan the board, it clears. Okay. Another aspect of the software client is the ability to perform transient analysis, so kind of like an oscilloscope, where I select an individual row to graph, and then I can graph it at 1 kilohertz. So this is useful if I need a time series of perhaps a sensor. In this example, I'll be graphing a potentiometer circuit that I built. Okay, so I've shown some simple components and simple checker functions, but we can extend that to working with integrated circuit packages. So these IC packages are often difficult, especially for beginners to debug, because they're literally black boxes. But by using their data sheets, we can generate checkers that know about the pins of those black boxes. So for this example, I've used an op-amp, which is a common maker element to amplify sensor output, for instance. Here, by tying its internal pin function to that package on the virtual breadboard, I get the ability to tell the user when they haven't supplied power to the correct pin. So it's common for a user to not know which pins of an IC package are essential to operation versus what they think is normal just for their circuit. So here we can tell them. We could extend that to even more complicated components. So this is an ultrasonic rangefinder from SparkFun. And by placing that on the board, we've used its data sheet to know about what the pin functionality. And now when I click the component, it highlights as shown, and I get a new option to graph it. So when I click that button, it automatically configures the oscilloscope to read from the correct output pin of the sensor. It also scales the y-axis to be in the correct unit of inches based on the datasheet scale factor. So I've saved the user a bunch of time by not having to have them comb through the datasheet and look for the correct scale factor, what the output means. Okay, and how do we do all this? At a high level, we have a breadboard. We've instrumented the entire thing. The information goes through a multiplexer scan chain on a custom PCB to a microcontroller with an ADC, and that's the CC3200 in our case. And then that data is sent back to the LED bars or to the software client. This is the Toastboard PCB. You can see that the breadboard actually fixes directly onto those pads on the left, and the whole thing acts as a shield for the CC3200. Okay, data from the breadboard is routed through this multiplexer scan chain, so that's how we access all 48 rows of the breadboard through one ADC on the CC3200. It's measured at this ADC pull-down network, and this is a float detection chain, which I'll explain now. So, what is a floating row? A floating row is not connected through any conductive path to power or ground. So if you've ever taken an analog read of an empty pin, you might have seen a random output, and that's what a floating row would do. However, in our case, we have that ADC pull-down network. So in order to make our measurements, we actually pull those nodes down to ground. That means that if we make a reading, we'll read it as ground. So with our float detection scheme, this is what we get, that nice clean representation of the circuit. Without our float detection scheme, this is what you'd get. So we've really ruined the clarity by getting those spurious ground readings. And this is how we do it. So concretely, this is what happens with no float detection chain. We read a floating row, and the pull-down network reads 0 volts at the ADC. When we add this, we can still detect that the row is actually at ground, because when we close that top switch, it still reads 0 volts at the ADC. When we read a floating row, however, closing that top switch puts a predictable voltage at the ADC, so now we've filtered out which rows are actually floating. So to make that a non-invasive form of scanning, we have to follow this flowchart, where we scan the rows of the breadboard. If it's above 0 volts, we display it as a real voltage. If it's at 0 volts, we scan it again with the float detection chain. Now if it's above 0 volts, we know it's actually a floating row and we display nothing. But if it's at 0 volts again, it's a ground row. So we've tried to make our instrumentation non-invasive so it doesn't influence user circuits, but we also want to make our software system extensible so you can add functionality. And we do that through making a pretty simple code base where it's written in JavaScript for your components and your component testers. And you can just get voltages at rows of your breadboard and compare them to component pins. You can also load schematics. So instead of using that point-and-click interface, you can just download a schematic and it'll populate your board. So you can imagine if you wrote a tutorial on the internet and you uploaded a schematic with that, you could have the user download it, populate their board with it, and then follow along through the construction. So you could help them with debugging. And there's some errors on the right. You may notice that's because there are no scans of the breadboard yet. We put this system in the hands of 7 users for an informal study. 4 of them were complete novices who had little to no circuit background. One was an intermediate person who had just finished a class in in electronics. And 2 were experts who were graduate students who had actually taught introductory electronics courses. Each of the 7 users were given 3 tasks. The first was to debug a circuit given an initially populated software client. So they had those virtual components already put on the board for them. The second was to debug a circuit given an initially blank software client. The third was to build and debug their own circuit. So if they didn't make an error while building a circuit, we introduced one for them. Some highlights from the user study. One novice noted that when a checker function told them they may have reversed their LED, they said, "I didn't know that was a thing." So we potentially saved them infinite time because they would never form that hypothesis in the first place, but we guided them to the correct answer. The experts had interesting points. One noted that the system would be like training wheels, perfectly suited for an introductory course. So that was encouraging. The other, however, worried that users would become over-reliant on the testers, on those checker functions, saying that you don't even have to think about it. It thinks about it for you. And that leads us to the limitations of our current system. So one, in hardware purely, is that we don't allow the user to supply an arbitrary power to the circuit. And this has to do with isolating our measurement circuitry from the user circuit. The second is that populating the virtual circuits can be cumbersome. And this was feedback we got from that user study, was that sometimes they didn't want to drag those virtual components onto the breadboard. Third is that checker functions can be too simplistic for some more expert users. So if you use a component in a non-conventional way, it might raise an error, and it might not actually be a mistake. Fourth is that we could actually overload the user with those error functions. So you can imagine one mistake in your circuit will propagate a bunch of errors to the rest of the circuit. And then you'll have all those checker functions telling you what to try to fix. And right now there's no way to weigh which one is the most likely mistake. Where do we want to take this work? As that expert user noted, we should take it to an extended user study where the Toastboard is distributed to an introductory course. It'd be nice if we can auto-generate some checkers. So to flesh out our set of checker functions, if we could parse through data sheets and automatically create a checker function for an IC package, it'd be a big way to expand our library. There's a lot of hardware development to do. We need more breadboard real estate. It'd be nice to have arbitrary power rails from the user input, as I said, and a smaller form factor. But finally, a lot of physical computing projects involve an Arduino or a microcontroller on the side. So wouldn't it be interesting if we could help the user debug their code alongside their circuit in an IDE that might look something like this, where you have a standard code debugger on the right, and it's paired with the physical measurements on the left. And that would open up a whole new suite of error functions that we can check, and we can make sure that that interface between the circuit and the code is clean. So in summary, the Toastboard is a tool that eliminates point measurements from debugging. It automatically diagnoses common errors in circuits, provides visual feedback while they're building the circuit, and it also preserves the core experience because they're using a breadboard. And conceptually, how we do that is we instrument the entire user circuit and provide all the measurements to them with low effort on their part. We combine those physical measurements with virtual models so that we can suggest common ways to fix their circuit. And that's my talk. Thank you very much.
Hi, Roshan from KU University. Very nice work. And I'm just wondering, like one of the most common errors is to accidentally connect the power and the ground together. In this case, how would it work? Because usually it would short out the voltage and like bring it down to zero, and maybe the whole circuit doesn't work.
Yeah, that's a great question. So the question is, if they accidentally short power to ground, what happens? Currently, because power is supplied through the USB port of your computer, it'll automatically shut down the power rails, and nothing horrible will happen. That's definitely, future work would be fusing the power rails so that it would not mess with your circuit at all. Doesn't break the board now, because that definitely happened during the user study. Yeah.
Darren Light, Actual Labs. It looks like you've done a lot of great work here, and I'm looking at this, and I can see your vision here. I can see the utility in IntraLab. As an experienced double E building circuits, this scares the hell out of me. I remember the first class, Electronics 101 at MIT, and the professor goes through all Ohm's law, has a resistor there, his little giant meter to show to the lecture hall, and deliberately burns up the resistor just to show us that the equations don't do what they're supposed to do. I have spent I don't know how many months in electronics labs with undergrads trying to showing them how to debug and everything. That debugging skill, from ground zero with a TA there, is vital to get someone to actually be able to do electronics eventually at a professional level. At an undergrad level, as a training wheel, maybe for a first course, I can see this. But I'd have to go along with that other expert who had that opinion there that people are going to become over-reliant on this. A lot of the circuitry that is in that, I love the fact that you've gone and done things to look for floating parts. That's excellent work on there, because it actually makes this useful, but it's going to interfere with some kinds of circuits, like op amps that are expecting extremely high impedances and expecting things not to mess it up. Where do you see this going other than a very intro electronics lab?
That's great feedback. So what circuits I'll take that in parts. What circuits does this influence? Right, higher frequency AC circuits probably not function as intended if they're high enough frequency. So I made an op-amp circuit, and it did work on this. And the idea is that the instrumentation is isolated by default from the user circuit through those passgate multiplexers. So unless I'm actively scanning the board, it shouldn't make that much of a difference for most low-frequency operations. Where do I see this going? I understand the sentiment of worrying that people won't develop that debugging intuition. I think that we also pose this more as a way to help people who don't have a future in electrical engineering or have a traditional background at all still build those cool projects that I showed in those pictures, like the physical computing projects made by computer scientists maybe, and this could be an accelerator to help them get those accomplished. I still think it's a valuable education tool, and those features aren't there by default. You have to get them. So if you want to turn them off, you can do that for your class. If you just want those measurement capabilities, that's all you can do if that's what you want. I think it's a very valid point, and it definitely requires thought of what we do with that.